In this section 5, we will deal with the Lagrange multiplier method, the 3 last subsections that deal with inequality constraints and the Karush-Kuhn-Tucker conditions are there for your information only. So, as mentioned before, we will leave the inequality constraints aside, right? This is treated in the course, but this is for your information only. So we'll find the minimum of a function that is no longer linear. It can be non-linear, subject to equality constraints. There can be up to m equality constraints, and the functions gi are also potentially non-linear. So this is what is on the menu of this section. We'll talk about the gradient. This has been introduced before. We have worked with the gradient vector, and then we'll look at the directional derivative, which is linked to the gradient vector. Then we'll look at constraint optimization with equality constraints, and this will lead to an unconstrained minimization of the so-called Lagrangian function. Right? We'll treat single constraints, multiple constraints, and then we'll look at examples. Let us start with the concept of directional derivative. We work with a function f of x, where x lives in Rn, right? And f of x is a scalar function, so it goes from Rn to R. The directional derivative of this function at a given point A in the direction u, and u here is a unit vector, is defined as follows. And as you can see, it's a vector form of the usual derivative that you know from previous courses, right? So this directional derivative in this direction u is the rate, you can see it from the formula, at which the function changes in the direction of u, and it is denoted as follows. So we use the nabla, and since we have to indicate in which direction this directional derivative is taken, we have to add here the vector u. Well, this directional derivative is linked to the gradient vector, well, evaluated at the same point A. Remember that the gradient vector yields the direction in which the function increases most quickly. So you can obtain the directional derivative from the scalar product of the gradient evaluated at the point A and the unit vector u. Well, let us have a look at this concept of directional derivative for a function of two variables x1 and x2, so that we can represent x in the x1 x2 plane, and we'll have a separate axis for f of x, and we have, well, a point A, right? And corresponding to A, we have a value f of A. So what we can now do is have a look at a change in the direction x1. So this is represented here by a unit vector in the direction of x1, and what we'll do is take a small step h, and of course this will induce a change in f of x, and we'll assume here that it is positive, right? And what we'll have here is a change that is the partial derivative of f of x with respect to x1 times h, right? So the ratio of this length over here over this length over here is the partial derivative of f with respect to x1. So we can say that the partial derivative of f with respect to x1 is really the directional derivative in the direction of this unit vector in the direction of x1 of f, right? So this is the partial derivative of f with respect to x1. Of course, what we have done, we can do it in the direction x2, right? So here we have a unit vector in the direction x2. We'll take a small step h in this direction, and this will also produce a change in f of x, and we'll assume this time that it is negative, right? And this one over here is the partial derivative of f with respect to x2 times h, right? So the ratio of this change over this change over here is the partial derivative of f with respect to x2. So you can see this partial derivative with respect to x2 as the directional derivative in the direction 1x2 of f of x, right? And so this is the partial derivative of f of x with respect to x2. So of course what we have done, we can do it in another direction than just x1 or x2. So we can define a vector, right? And again we'll make it a unit vector. We'll define it u, and we can write its coordinates in this set of vectors. So it will be u x1 1x1 plus u x2 1x2, right? So what you can do now is take a small step h in this direction, right? So h times this vector will be h u x1 1x1 plus h u x2 1x2. So it's as if you're taking a step in first this direction here and then this direction over here. So this will produce a change. Let us say that it's positive, and it will be, well, h u x1 times the partial derivative of the function with respect to x1. So it will be h u x1 partial derivative of f with respect to x1, right? And then we'll have to do something similar because we are also doing a change in this direction, right? So it will be plus h u x2 partial derivative of f with respect to x2. And this, of course, you can rewrite. You can write it as h times u x1 partial derivative of f with respect to x1 plus u x2 partial derivative of f with respect to x2, right? And this one you can rewrite as h, and then you'll take, because you have here the gradient of f, right? This is a vector scalar product with the vector u, right? So you can see here that you will have a change here, and the ratio of this change with respect to the change that you've done in this direction will be the directional derivative in this direction u over here, right? And you can see that you can write it in terms of the gradient and scalar product with the direction. So this is really the directional derivative of f in the direction of u. We have defined the directional derivative or direction gradient as the rate at which the function changes in the direction u. This directional derivative is the scalar product of the gradient vector and the direction vector. Scalar product means that this directional derivative is, of course, a scalar quantity. This scalar product can be written in terms of the magnitude of the gradient vector, the magnitude of the vector u, but since it is unit, this is 1, right? And the angle in between the gradient vector and the direction u. And this is why you can write the directional derivative in terms of the magnitude of the gradient vector. This is this one, and the cosine of the angle between the gradient vector and the direction vector u. Of course, cosine theta assumes values in between 1 and -1, so we'll treat 3 special cases. Theta is equal to 0 corresponds to cosine theta is equal to 1. Theta is equal to pi. This corresponds to cosine theta is equal to -1, and then we'll consider the case where theta is plus minus pi over 2, and this corresponds to cosine theta is equal to 0. Well, we have seen that the directional derivative of f in the direction of u evaluated in A is, well, the magnitude of the gradient evaluated in A times the cosine of theta, and theta is the angle that the gradient and the direction u make. So if you take theta is equal to 0, this means that u points in the direction of the gradient, and as you can see, cosine theta is 1, we'll have that the rate of change in that direction will take its maximum value because it will be the magnitude of the gradient evaluated in A, and that's something that is non-negative. Well, this corresponds to the direction of steepest ascent of f of x at A. If we take theta is equal to pi, then the direction u points in the opposite direction of the gradient, and the rate of change will take its minimum value. Indeed, cosine theta will be -1. So the rate of change in that direction will be negative or 0, and this is the direction of steepest descent of f of x at the point A. If we take theta is equal to plus or minus pi over 2, this means that, well, u points in a direction that is perpendicular to the gradient, and of course cosine theta will be 0, so the rate of change in that direction is 0. If we take theta in between minus pi over 2 and pi over 2, and we will not consider the limits pi over 2 and minus pi over 2, well, the cosine will be positive, right? And this quantity over here, which is the directional derivative, will be an ascent direction because the scalar product is positive. We know this because the cosine, when theta is in this range, is positive. In this range over here, the cosine will be negative, right? So the directional derivative in directions that correspond to those theta here will be negative, and this will therefore correspond to descent directions. We have just seen that if the direction u is such that the directional derivative of f in this direction is 0, then this vector is perpendicular to the gradient. But this direction is then such that the rate of change of f in that direction is 0. This must mean that in this direction f is not changing and that you are therefore on a level curve, right? So in this direction of u, you're traveling on a level curve, and you can see that this direction is perpendicular to the gradient, so you can see that the gradient is indeed perpendicular to the level curve of f. So another way to see this is as follows. Let us assume that r of t, and this will be a kind of position vector x1t up to xnt, is a level curve. So this means that, well, f evaluated on this curve, and this is true for all t, is equal to some constant, right? Well, if you take the derivative of this one here with respect to time, this means that this will produce 0, right? And this is equivalent to, well, we'll have to take the chain rule. We'll have to take the partial derivative of f with respect to x1 dx1 dt plus the partial derivative of f with respect to x2 dx2 dt, and we do this for every component, so up to the partial derivative of f with respect to xn dxn dt, and this is 0, right? But this is really the scalar product of the gradient of f with the instantaneous direction of motion v, and this is also 0 here, and v of course is dx1 dt up to dxn dt, right? V is tangent to the level curve, right? So this means that the gradient has to be perpendicular to the level curve, because, well, the scalar product of the gradient with a vector that is tangent to the level curve is 0, and therefore the gradient of f must be perpendicular to the level curve. Well, let us consider the function f of x, that is a scalar function that acts on a vector x that is in R square, so 2 variables, and as you can see we have to work in 3 dimensions to represent this function. You can see here the 3-dimensional surface, and we have shown here, well, several of the level curves in this 3-dimensional plot. What is often done is to use a level plot of the function or a contour plot of the function, and this is a way to represent the 3-dimensional surface on a 2-dimensional plane. The contours that you see over here, or the levels, are sometimes called also, well, f of x slices or iso-response values. Besides the level curves, you also have information about the gradients in some of the points. Remember that the gradient is the direction of steepest ascent, we'll now concentrate on one point on a level curve here in gray with its gradient vector and zoom in on this. Well, this is the point that we had considered, right? And this is the direction of the gradient, so this is the direction of steepest ascent. You can see that if we draw the tangent here to the level curve that you have over here, you can see that the gradient is indeed perpendicular to the level curve. Directions that are perpendicular to the gradient, for instance this one and this one, correspond to directions where the directional derivative is 0. This is kind of logical. If you take a small step in this direction, you will stay on the level curve, right? Notice that the directions here given in blue are all directions of ascent, right? And this will be the case as long as the angle is larger than minus pi over 2 and smaller than pi over 2. If we now take a direction that corresponds to theta is equal to pi, we'll have a direction that is opposite to the gradient and we'll have a direction of steepest descent. But the directions that are shown now are all directions that correspond to descent, and this will be the case as long as theta is larger than pi over 2 and smaller than 3 pi over 2. Well, now that we have reviewed the concept of a gradient and a directional derivative, we are ready to tackle the problem of minimizing a function that can be potentially non-linear, subject to a single equality constraint. Gx is equal to 0, and here also g of x is a potentially non-linear function. The constraint minimization problem we have to deal with is the minimization of f of x subject to g of x is equal to 0. So we have an equality constraint, and we'll look at this in the special case where x has 2 components, so x is in r square, because then we can represent everything in 3 dimensions. So we have x1, x2, these are the components of x, and here you have, well, the z axis, right? And what you see here is the surface z is equal to f of x here, and this is of course a surface that is represented in 3 dimensions, right? If we now look at the constraints, g of x is equal to 0, well, this defines a curve in r square. So we can look in the x1, x2 plane, and g of x is equal to 0, well, defines a curve that we'll call C, and a point that lies on this curve represents an allowable value for x in the evaluation and minimization of the function f of x, right? Well, associated to a point on this curve, right, you have a point that is lying on the surface z is equal to f of x, right? So you can consider the image of this curve through the function f of x, and you'll define a curve d here that is really z is equal to f of x, where x is constrained to live in this curve C over here, right? And this curve D, of course, is defined in R cube, right? So it's a three-dimensional curve, right? And of course, we are interested in finding the minimum of f of x with x constraint on this curve over here. So this means that we are kind of looking for the minimum value on this curve D. This means the point with the smallest component z, and it will be a point that will be located somewhere over here. The point here on this curve D with the smallest z component is the one that corresponds to our minimization problem, and the corresponding x star is the one we are looking for. This is the minimizing argument, right? And in this point x star, the rate of change of f of x in the direction tangent to the curve C over here is 0. This means that the directional derivative of f of x in this direction tangent to C is 0. So the first thing that we should do is define this direction tangent to the curve C in x star, and well, it is defined by this equation, right? Because we know that the tangent vector, right, is perpendicular to the gradient of g of x in x star. So this is how you obtain this direction tangent to the curve C in x star. And now what we have to do is impose that the directional derivative of f of x in this direction that we have just defined is 0, right? This is the directional derivative, and it must be 0, and we have seen that the directional derivative of f in a given direction, well, that's the gradient in x star times this direction, right? And here this direction is shown over here. It's a direction of steepest ascent, and this direction of steepest ascent should be perpendicular to the vector that is tangent to the curve C over here, to ensure that this directional derivative in this direction V is 0. Well, we just arrived at the conclusion that we are looking for an x star where the directional derivative of f in the direction V tangent to the curve C is equal to 0, and this imposes this equation over here, right? And a direction that is tangent to the curve C in the point x star is defined by this equation over here, and this is imposing a second constraint. So we're looking for an x star where V has both properties, and you can see that V is perpendicular to the gradient of G and V is perpendicular to the gradient of F, right? So this is equivalent to looking for an x star where the gradient of F is parallel to the gradient of G. So there will be in between those two here a scalar, right, minus lambda star, and lambda star is called the Lagrange multiplier associated to x star. So depending on the sign of lambda star, the gradient of f and g should point in the same direction or in opposite directions. So really we're looking for an x star where the gradient of g and the gradient of f are pointing in the same direction or in opposite directions. Note that the gradient of f is perpendicular to the level curve and that the gradient of g is perpendicular to gx is equal to 0. So we are looking also for a point x star, this is equivalent, where the level curve of f is tangent to gx is equal to 0. Another perspective is to parameterize c, the locus of all points, such that g of x is equal to 0 as a function of time. So we'll write x of t as follows: x1 of t up to xn of t, right? And we can use the following tutorial example that we'll use next to illustrate this. So here we have this constraint, gx is equal to 0, and if you look at this, well, you will see that the curve C will be a circle centered at the origin in the x1, x2 plane, right? And it will have a radius square root of 2. So here x of t can easily be parameterized as follows. So x1 of t and x2 of t, there are only two components, right? And it will be square root of 2 cosine t and square root of 2 sine t, right? And if you let t evolve, this will generate a circle centered at the origin with a radius square root of 2. So let us come back to our other perspective. By the way, this will work for x in Rn. We have parameterized c as a vector that is changing with time, and as we move over c, we evaluate the function f x of t, and where we'll have the minimum is a point where the rate of change of f of x of t, where x of t is moving on c, is 0. So what we have to do is to compute the time derivative, and we have already computed this time derivative in another example for another purpose, and this time derivative is simply the gradient of f times, well, this instantaneous velocity vector, and this rate of change is 0, so this is what we impose, right? While we are moving on c, we have the constraint g of x of t is equal to 0 for all t. So what we can do is compute the time derivative of this one, and if you do this, this is what you'll obtain. And you can see that again we're looking for a critical point where the vector v is both perpendicular to the gradient of f and the gradient of g. So we're looking for a critical point x star where the gradient of f and the gradient of g are aligned, and that there is some scalar lambda star for which this equality holds. We have shown in two different ways that in a point x star, that is the solution of our minimization problem of f of x subject to g of x is equal to 0, well, the gradient of f of x and g of x are aligned. We are now going to show it using this tutorial example. The tutorial example is very simple so that we can represent everything, and we minimize an objective function that is linear in x1 and x2, so it's simply x1 plus x2, and the equality constraint constrains x1 and x2 to live on a circle centered at the origin and this circle has a radius of square root of 2. Well, this example is so simple that we can represent everything in the x1, x2 plane. So we can start by representing the level curves of f of x is equal to x1 plus x2. Since f of x is a linear function, these level curves are lines, okay? And you can see level sets associated to the values 2, 1, 0, minus 1, and minus 2. What we can also show is the feasible region, and this feasible region shown here in red corresponds, as announced before, to a circle centered in 0 and of a radius square root of 2. We will now start from a feasible point x star and try to see under which conditions we have optimality. So we'll be looking for a direction delta v, and this direction must be such that, well, if you take a small step in this direction, well, you stay on the curve gx is equal to 0, and this is because of the constraints. And if you take a small step in this direction, well, we have a new solution with a cost that is smaller as the cost in x star. Let us now look at decreasing the cost. The gradient of f corresponds to the direction of steepest ascent, so minus the gradient corresponds to a direction of steepest descent, right? So what we'll do is compute the gradient. Remember that f of x is simply x1 plus x2, so the gradient of f is a vector. First element is the partial derivative of f with respect to x1, so that's 1 over here, and the second element is the partial derivative of f with respect to x2, so that's a 1 as well. So notice that this gradient is independent of x1 and x2, and this gradient will be pointing in this direction, right? This is the direction of steepest ascent, and this is the direction of steepest descent. And indeed, in our feasible point x star, the direction of steepest descent is given by this vector over here that corresponds to minus the gradient of f. Notice that the gradient is indeed perpendicular to the level curves, and in this case these level curves are level lines. Well, notice that the direction delta v is also a direction of descent. Remember that the gradient is given by this vector over here, and directions of descent are directions where the angle that the vector makes with the gradient is larger than pi over 2 and smaller than 3 pi over 2. So vectors that are like this all correspond to descent directions. So in order to select a descent direction, well, we have to make sure that delta v obeys this equation over here, and this will make sure that if you take a step in this direction delta v, the cost will decrease. Well, notice also that with the new solution we have to still meet the criterion g of x is equal to 0, so we have to remain on the constraint curve gx is equal to 0. Here g of x is really x1 square plus x2 square minus 2 is equal to 0. So what we can do is compute the gradient of g of x, and we have to first compute the partial derivative with respect to x1. That's 2x1, so this is the first element in the gradient, and the second one is the partial derivative with respect to x2, so this will provide 2x2 over here. And as you can see here, this gradient, when you have a point on the curve, is pointing outward, right? So it is perpendicular to the tangent, and this is true in every point, right? So it is also true in this point. So this is the gradient that is shown over here, and if you take a small step in a direction that is perpendicular to the gradient, then you're going to stay on the curve g of x is equal to 0. So in order to remain on the curve, you need to select a delta v that is such that if you take the scalar product with the gradient, you have 0, and this is taking a small step in a direction that is perpendicular to the gradient. So let us look at the possibility to decrease the cost and at the same time remain on the curve g of x is equal to 0. So here in red, what you've got is the gradient of g for different feasible points on g of x is equal to 0, and here in blue you have minus the gradient of f for these same feasible points. Remember that minus the gradient of f corresponds to the direction of steepest descent, but of course there will also be other directions of descent, right? Remember that this is the gradient of f, right? And directions that are such that the angle is larger than pi over 2 and smaller than 3 pi over 2, as indicated over here, all correspond to directions of descent, right? So what we'll do now is consider different points and try to see if they correspond to a global minimum, right? In this point, you can see that if you take a direction that is perpendicular to the gradient of g, well, this will correspond to a direction of descent. So if you take a small step in that direction, you'll stay on g of x is equal to 0, so you'll meet the constraints, and at the same time you will decrease the cost. So this is not a global minimum, right? Let us take this point over here. And here again, if you take a small step in a direction that is perpendicular to the gradient of g, well, you will have a direction of descent. So in this point, you can take a step and stay on the curve gx is equal to 0 while decreasing the cost. So this is not the global minimum, right? So in this point over here, right, you can see that if you take a small step perpendicular to the gradient of g here shown in red, you will stay on the curve g of x is equal to 0, but you will no longer have a direction of descent, right? So here, if you move from this point, it is not possible to stay on the curve g of x is equal to 0 and at the same time decrease the function. So here we have a critical minimum point, and it corresponds here to x1 is equal to -1 and x2 is equal to -1. In this point here, we'll call it x star, we have that the gradient of f evaluated in x star is equal to minus lambda star times the gradient of g evaluated at that same point. You can see indeed that minus the gradient of f, that's the one given in blue, is aligned with the gradient of g. And here we have lambda star is positive. This will correspond to a critical minimum point. You also have a critical maximum point, right? At this point here, if you take a small step that will keep you on the curve, the red curve, gx is equal to 0, you will no longer be able to increase the cost, right? And in this case, you can see that the gradient of g is indeed, well, pointing in the same direction as the gradient of f. Remember that the gradient of f is pointing in this direction. This one here is minus the gradient of f, right? So in this case, we'll have a lambda star that is negative, and this will correspond to this critical maximum point. We have seen in the tutorial example that for every feasible point x star that lies on gx is equal to 0, if you select a small delta v that is orthogonal to the gradient, it will ensure that, well, you stay on the curve gx is equal to 0. And if you select such a delta v, well, a delta v will also be a direction that will allow you to decrease the cost. At a critical minimum point, well, the delta v that you select to stay on gx is equal to 0 is a delta v that will no longer allow you to decrease the cost, because you have this relation, right? So this is how you say this mathematically. In words, it is impossible to move away from x star on gx is equal to 0 while decreasing the objective function. And we have found this relation over here for some lambda star. Of course, you can also have a critical maximization point, right? And, well, in our case, in our tutorial example, the critical minimum point was a global minimum, a global constraint minimum, right? Whereas the critical maximization point was a global constraint maximum, right? But in general, a critical point does not necessarily correspond to a constraint minimum, as this Lagrange method, this condition here, provides necessary but not sufficient condition for a local minimum. And this is because this is only based on, well, first order information about the gradient. In order to find a sufficient condition, we would have to consider the Hessian. We now arrive at a very important result, which is at the basis of the Lagrange multiplier method, and it is for problems where you minimize an objective function f of x subject to a single equality constraint g of x is equal to 0. We'll assume here that x star is a local minimum of this constraint problem. What you can then do is define the so-called Lagrangian function, and this Lagrangian function is defined as follows. It is the original objective function plus lambda, and this is the Lagrange multiplier, times the objective function. Well, this statement says that if this constraint problem, right, has a local minimizer x star, well, then there exists a lambda star such as the gradient of the Lagrangian is 0. So there exists an x star and a lambda star such that this Lagrangian function has a local minimum. We have transformed the constraint minimization problem into an unconstrained minimization of this Lagrangian function. So notice that in x star, g of x star is equal to 0. So indeed the Lagrangian function evaluated in x star lambda star, since this term is 0 here in x star, will be equal to the function evaluated at x star as stated over here. If you define the single equality constraint problem that you have over here and define the Lagrangian function as follows, well, then we have just seen that if x star is a local minimum to this constraint problem, well, then there exists a lambda star such that the gradient of this Lagrangian function evaluated in x star lambda star is equal to 0. In this gradient, of course, you have the partial derivatives with respect to x, right, and the partial derivative with respect to lambda, which is the Lagrange multiplier. If we only consider in this equation the partial derivatives with respect to x, this leads to this equation, right? And if we only consider the partial derivative with respect to lambda in this equation, this is what you obtain. And you can see that this first equation, if you apply it to the Lagrangian function, really is equivalent to this equation here, that is simply saying that at the critical point the gradient of f and the gradient of g are aligned, right? And this second equation, so the gradient with respect to lambda, will simply produce g of x. So this is encoding that g of x is equal to 0 at the critical point. As said before, not all critical points and the solutions to these two equations will yield a solution to the original problem, okay? Because this method of Lagrange multipliers provides a necessary but not sufficient condition for optimality in constraint minimization problems. We have only considered first order information about the gradients. To obtain sufficient conditions, you would have to add conditions on the Hessian. Well, if you have a constraint problem with multiple equality constraints, you can use the same trick, right? So here we have m constraints and the number of variables is n because x is in Rn, right? So what you can do is define the Lagrangian function. It's the original objective function where you add a number of terms, and each term is, well, a constraint, an equality constraint multiplied by a Lagrange multiplier. So this function here, this Lagrangian function, will be depending on n plus m variables, right? N variables coming from the objective functions and m variables coming from the Lagrange multipliers. Well, if this constrained optimization problem has a local minimizer, well, then this Lagrangian function has a minimum in the sense that the gradient of this lambda evaluated in x star lambda star is equal to 0. And the difference with the preceding case is that lambda star here now is a vector containing all the Lagrange multipliers. But again, we have transformed a constraint minimization problem with equality constraints into an unconstrained minimization of the Lagrangian function, right? And this gradient can be rewritten as follows. And again, these m last equations here will simply encode the fact that at the optimum, well, these equality constraints have to be met. Well, let us have a look at an example of a constraint optimization problem. This is the objective function. So we have three variables, n is equal to 3, and we have two equality constraints. So m is equal to 2. We'll have two Lagrange multipliers. So the equality constraints we have to write as g1x is equal to 0 and g2x is equal to 0. And so that we have the same formulation as in the slides, right? So we have to take the one to the other side. And indeed, g1 of x is this one here, minus 1, right? Do not forget to do this at the time of the exam, because this is a failure or a mistake that I often see. So we can transform this constraint optimization problem into the unconstrained optimization of the Lagrangian function. So we take the objective function f of x, we add lambda 1 times the first constraint. Well, it's not the first constraint, it's the function that is in the first constraint, plus lambda 2 g2 of x, and this is what you obtain. And now a local minimizer of this problem will be a local minimizer of this problem, and since this problem is unconstrained, we can simply compute the partial derivatives of the Lagrangian function with respect to the three original variables and the two Lagrange multipliers. So if we take the partial derivative of the Lagrange with respect to x1, you will have 2x1 here plus lambda 1, and over here plus lambda 2. Partial derivative of the Lagrange with respect to x2 will have 4x2. It's the partial derivative of this one, and here this one will lead to 2 lambda 1, and this one over here will lead to minus 2 lambda 2, right? And then finally the partial derivative with respect to x3 will have 2x3. Here we'll have plus 3 lambda 1 and plus lambda 2. If you take the partial derivative with respect to lambda 1, well, you'll simply have g1 of x, and if you take the partial derivative with respect to lambda 2, you'll have g2 of x. This will always be the case, and what you will have to do, since you're looking for a local minimizer, is to impose that these partial derivatives are 0. So these are the 5 conditions for a critical point that you obtain. As you can see, the two last equations simply are the linear constraints that we had in our original problem. These 5 conditions are equivalent to the gradient of the Lagrangian function is equal to 0, right? As you can see, this system of equations here is not that difficult. This is because of the problem. If you have, for instance, a nonlinear function with nonlinear equality constraints, the system of equations that you might have to solve might be, well, substantially more complicated. So there are several ways to arrive at the solution. I think that here the easiest way to go is to look at the three first equations and write x1, for instance, as a function of lambda 1 and lambda 2. So in this case it will be minus lambda 1 minus lambda 2 divided by 2. You do something similar for x2. You'll have 2 lambda 2 minus 2 lambda 1 over 4, and you'll do something similar for x3. So this will be minus 3 lambda 1 minus lambda 2 over 2, right? And then you inject those three in these two last equations, and you'll have a system of equations with two unknowns, and the unknowns will be lambda 1 and lambda 2. And since you have two equations and two unknowns, well, you can solve this quite easily. Indeed, as announced, you obtain a system of two equations with two unknowns. The solutions are given over here. I'll leave the calculations, and of course we are not interested in lambda star and lambda 2 star, but we are interested in, well, the solution in terms of x1, x2 and x3. So what you'll do is inject those optimal Lagrange multipliers in here, and you obtain the optimal solution in terms of x1, x2 and x3. And if you do the computations, these are the optimal solutions that you obtain. I'll leave you the calculations, and if you inject them in the cost, this is the optimal cost that you get. This is a global minimum. This cannot be a maximum, because this function over here can take arbitrary large values while letting x1 and x2 and x3 grow while satisfying the two constraints. So here we have a global minimum. Well, as usual, it's possible to check the result with a Matlab. So we'll use a numerical method over here. So the first thing that you have to do is construct a function that encodes the objective function, and then you have to construct a function that constructs the inequalities, right? There are none over here, and the equality constraints, right? And then you can use the function fmin con for constraints. Well, as usual, you should have a look at the help function associated with the function, and as usual, well, it's probably best to have a look at the reference documentation, and over here you have the syntax, right? And the syntax that has been used is this one over here. So the objective function has been introduced using this function over here, and the nonlinear constraints have been added using this function over here, and then it's explained over here how to write the objective function and how to write the function for the constraints. And you have indeed nonlinear inequality constraints of the type smaller or equal, or nonlinear equality constraints. This is the code that you have to run. My fun and my con have been defined in the slides. Notice also that we have here a starting point for the numerical method. We'll come back to this in the next section, where we'll talk about numerical optimization, but for problems without constraints. So let us run this code, and this is indeed what you obtain. And if you go and look, you will see that the third solution was 10 over 11, and as you can see, this corresponds. So you can check your results with Matlab.